Yeah, welcome again for those joining the line here. We're just holding for one more moment while we get folks logged into the WebEx. I see a steady stream of people coming in here. But I will kind of start with some of the logistics here for the WebEx. Just for folks' awareness, as you come in, you'll automatically be muted. So you'll see a display screen on the top of your window that looks much like what you see on the screen share here. For ability to unmute and start videos. We are anticipating maybe up to 100 folks today, 100 people on the line. So we do ask that people just remain on mute and use the chat function. We've got people that are going to monitor the chat, and we'll try to answer questions in real time. So with that, yeah, if you could just hang tight, we'll get rolling here in just a second, and we'll get going with the webinar. It looks like we got a pretty good attendance here, so I'm going to get started. So, yeah, welcome again. This is the Phosphorus Optimal Wetland Demonstration stakeholder webinar. So we're really excited to have good attendance on the line today to talk about this project in Defiance, Ohio. So welcome to the call. Just orientation for those that just jumped on, you will be automatically muted to the WebEx here as you join. But you should see the ability to chat up in the upper right, I believe, of your WebEx window as a chat bar. So feel free to use that for any questions as we move forward. But with that, we'll get going with today's webinar, and very excited to have good attendance today and a lot of folks on the line here. So I'll start off just a quick intro for myself, and then I'll introduce our team here in a moment. My name is Tim Noon. I'm a project manager for the U.S. Army Corps of Engineers out of the Buffalo District. I've got a great team supporting me here today, and I'll introduce them here in a moment. So we'll get going with the slides. All right, so this is the Phosphorus Optimal Wetland Demonstration Project, and really, this comes out of the problem of harmful algal blooms, specifically in the Great Lakes, Western Lake Erie Basin in particular, and the associated economic, human health, and habitat impacts that come from them. Our goal for you today on the line with us is to give you a really brief overview of what our project is, what this Phosphorus Optimal Wetland Demonstration Project is, because we realize we do have kind of two audiences here. We've got folks that we've been talking to about this project for several years, and there might be some newer people on the line who've never heard of the project. So we do want to give a basic overview of what the project is. But we want to specifically share some of the preliminary results that we're finding out of the research and monitoring that we've got ongoing on our demonstration wetland. And we also want to foster some opportunities to share and apply this research. Really, that's one of our main goals, is to do some technology transfer of the findings that we're gathering out there at the wetland. And try to relate those to other projects and efforts going on across the Great Lakes Basin or even beyond that. So the agenda today is we'll give that background. We'll talk about wetlands and phosphorus optimization. We'll specifically talk about the project in Defiance, Ohio, this demonstration wetland that we've got out there. The team will give an overview of what our preliminary results are, and then we'll try to foster a little bit of that discussion of translating science into action. And we'll take questions throughout via the chat, but we do ask that you hold any verbal questions, kind of remain on mute until the end of the presentation, when you can feel free to come off of mute and ask any additional questions. But really do encourage questions to be asked via the chat throughout the webinar here, because we do have team members that are on the line with us that'll be keeping an eye on that and be able to answer some of those questions. So again, yeah, the problem that our team is looking to address, right, is Great Lakes algal blooms and the linkages to excess phosphorus in Great Lakes tributaries. Our specific goals are to contribute to the Great Lakes Restoration Initiative, specifically Focus Area 3, non-point source pollution. Second, to optimize phosphorus retention on the landscape through research advancements. That's really what we're doing out here, is some research. And then lastly, demonstrate the potential for long-term sustainable nutrient reduction in the Maumee, but beyond that as well. And really, this all comes together as an opportunity to demonstrate some novel and innovative approaches And that's really what our team, our multi-agency team is engaged around here, and what we're going to be talking to you about today. This slide, a little bit confusing probably to look at, but a lot of information as well. But I just wanted to use this to sort of introduce the team that's going to be talking on this webinar today, and also to orient everyone to how we're sort of set up structurally here, right? So this project, as I mentioned, is a multi-agency effort. It is a research effort. So while we at the Corps of Engineers are coordinating this through the GLRI with our partners at the EPA, out of the Buffalo office here, our research is led by our Engineer Research and Development Center. Specifically, Jacob Berkowitz is on the line with us. Dr. Berkowitz is a soil scientist there at URTIC. He's going to be talking to you here shortly. We're also utilizing our contractors at LimnoTech, and we'll have Derek Schlee, a senior ecological engineer, on the line with us today. And our main federal partner in the project level is the U.S. Geological Survey. And we've got Chad Toussaint, a physical scientist there, on the line with us, and he'll be talking through the USGS components of it here today as well. So this is just kind of a snapshot of how structurally we're organized and kind of doing this research, and even, you know, the history of the project, building the wetland out there in Defiance, and doing the work over the next several years. Okay, so this is, you know, again, we're talking about the novel application of phosphorus optimization in a wetland setting to reduce nutrient loading into Great Lakes tributaries. We've got a long timeline, and the team is going to sort of speak to this, including some very detailed research-specific history for soil phosphorus storage capacity that started in about the 2013 timeframe that led us to this conceptualization and ultimately construction of a demonstration wetland out in Defiance, Ohio. And now we're in this monitoring and research phase, and this is going to take us out through 2026. We've just finished up the first year of that research phase, so we've got some preliminary findings to share here today. So with that, I'm going to turn it over to Dr. Jacob Berkowitz on the line with us. Jacob, if you got anything else you want to say to this slide, otherwise you just tell me when you want to advance. Oh, and one more note, Jacob, before we move forward too, is that we are recording the webinar today. That's for intended use afterwards to be able to put on a project website and share for those that weren't able to make it. So just a word of notice that this webinar is being recorded. So Jacob, I'll turn it over to you if you have anything else here.
Yeah, thank you, Tim. Great introduction, and thanks everybody online for joining. Again, please feel free to post questions in the chat, and I'll try and address them as I go through my presentation materials, and then we'll have ample time at the end, I hope, for some oral back and forth with the audience. So just to kind of wrap it up with this slide, you know, this project has been a process that's been going on for almost 10 years now. We've been working away at it. Kind of started with literature review, state of the science, and really trying to understand how wetlands fit within this context of nutrient reduction potential. And that is really built into the research framework that Tim shared. And, you know, really now this is the exciting part of the project. After years of planning and organization, you know, now we have a site that's been built out, and we're in a really positive posture to conduct research and monitoring. And really the purpose of the Defiance wetlands is, you know, to have a site for experimentation. And so it's a good opportunity to highlight chances to partner with those on the line to come out to the site and test ideas. And really we're moving into that kind of experimental phase of the project to help facilitate, you know, maximizing phosphorus reduction and nutrient reduction through the use of wetlands. And so we're very lucky through our project partnerships with GLRI and the EPA that we do have some long-term funding here. You can see the timeline for monitoring and research goes out all the way to 2026 and potentially beyond that. And so that really gives us an opportunity to do some valuable work here and build upon the previous studies. So with that, Tim, let's go to the next slide and talk a little bit about why we're so interested in implementing wetlands for nutrient reduction in the region. And the reason that I'm interested in wetlands, I'm a soil scientist who specializes in wetlands. And so, you know, the reason I find wetlands so intriguing It's because they provide such a wide variety and a high magnitude of ecological functions that benefit society. And we can utilize and manipulate wetlands in ways to really maximize those functions and the associated benefits. And so while we've seen the large-scale implementation of agricultural best management practices across many regions of the United States, including much of the Great Lakes, we're still failing to reach many of our, regional and continental scale targets for water quality improvement. And wetlands really fit uniquely within that best management practice framework because they have the unique capacity to both reduce nutrients, kind of in an edge of field scenario, but also after water has left the fields or left urban areas and entered the surface water. If we can get that water back in contact with wetlands and floodplains or depressions or other landscape positions, then we can get additional removal of nutrients, both in an edge of field context and kind of in a loaded situation. And so that's really a unique and dynamic property of wetlands that we don't see in some of the other available best management practices. So wetlands really do play a kind of a unique role in this situation. And additionally, especially when we look at places like northern Ohio, where the Defiance wetland is located, more than 90%, 95% of the wetlands that historically were in these areas have been extirpated from the landscape. And so if we can, utilize the wetland retention benefits of nutrient retention benefits of wetlands to do some wetland restoration, then we also see the delivery of co-benefits, things like habitat, the opportunities for recreation and education that we're seeing in places like Defiance. So it's a great story start to finish when we start to integrate wetlands into the system. The other reason that we want to use wetlands is that they've been shown to be very effective to reduce nutrients, and you can see some of the data in the central figure there. This is data from a 12-year study that we partnered with the Nature Conservancy to conduct at some treatment wetlands that they have constructed in Ohio. And you can see that, it's not uncommon for wetland systems to have cumulative phosphorus load reductions in the range of kind of 40 to 80%. So really good numbers there. And so in order to support this project in Defiance, we've been working with the Nature Conservancy and many other groups to look at the long-term nutrient reduction potential of wetlands. And we have a number of publications that you can see on the screen that speak to that and that are available open access for the public to investigate. There are also a lot of challenges and questions related to how we can best use wetlands for nutrient retention. And some of those are listed on the screen. There are many others, but the ones I would like to highlight include the fact that, many of kind of the ideal sites to build wetlands are hotspots for soil phosphorus because the landscape positions where we'd like to build wetlands oftentimes coincide with areas that have been heavily fertilized or received high phosphorus containing runoff over a number of years. So that's a limitation. Also, just by the nature of some of the phosphorus removal mechanisms are limited over time, and wetland systems do have a finite capacity to retain wetlands on the landscape. There are many logistical challenges associated with using wetlands for this, and one of them that always comes up is project cost. And so we're using our site at Defiance to better evaluate life cycle analysis for these systems so that we can provide our managers and decision makers with improved life cycle analysis to help maximize the use of the public's investment in terms of using wetlands for this purpose. And then the final two things I'll touch on is that, we're very much interested as a team in operational guidance. How do we help expand the use of wetlands by giving practitioners really practical guidance about how to build and operate these sites? And that's what's needed to try and scale up this use of wetlands in the Great Lakes region and elsewhere to have the biggest impact. Let's go to the next slide, Tim. So to support this effort, we, working with our partners at LimnoTech and others, have developed and proposed a 6-part framework for utilizing wetlands to optimize phosphorus retention. I'm not going to go through the details of the slide here, but I will reference the Journal of Great Lakes Research publication that's provided in the bottom, and that'll be again, highlighted in some of the tech transfer slides. But in general, if we're going to maximize wetland retention, we have to look at a watershed scale perspective and look at a combination of both off-site GIS-based measurements as well as on-site measurements to make sure that where we're constructing wetlands are appropriate places on the landscape that also have the physical chemical properties to maximize nutrient retention. And we did that with the Defiance wetland. We used this 6-part process to select, design, and build the site at Defiance, and we're now continuing through this stepwise deliberate process to communicate our findings at Defiance and continue to adaptively manage that site through our research framework. Let's go to the next slide, Tim. And then the final thing I'll touch on before we really get into the details of the actual build at Defiance that Derek's going to talk about are that we can also use both benchtop and mesocosm studies to help inform how to operate wetlands for nutrient retention. And so we've been doing this in the laboratory for a number of years, and we also have a Journal of Great Lakes publication that came out last year that talks about some of these benchtop and mesocosm results. And what we find is that environmental factors play a big role on the nutrient retention efficiency. So the graph that you see in the middle there, reflects the potential effect of soil temperature on phosphorus retention rate. And so these are things that we need to consider as the temperature changes over time and water quality parameters change over time. What sort of removal efficiencies can we expect when we see changes in temperature? Things like oxygen availability and holding times have a big impact on how much phosphorus was removed. And so if we want to get at those cost and life cycle analysis questions, we not only need to consider kind of the gross measurements, but also these environmental fluctuations related to how the sites are operated and how they will perform. And so there's a lot of information that we've pushed out already in terms of how to select, build, and now operate these sites to maximize phosphorus retention. And we're really, encouraged to see others in the region picking up pieces of those research products to inform how they're selecting, building, and operating sites moving forward across the Great Lakes region. And with that, Tim, let's go to the next one. I think I'll turn it over to Derek to talk about some of the specifics of the Defiance wetland.
Yeah, very good. Thank you, Jacob. So transitioning to how we arrived at this Defiance, Ohio wetland demonstration site for a moment. As Jacob was describing, really we started this process of a watershed analysis and public engagement piece, and that's depicted in the figure in the top right in the publication that Jacob described earlier. That was about 5.5 years ago now, and that began with some desktop geospatial analysis work at both the Maumee River watershed scale, as well as later finer spatial scales. We then pivoted into meetings with local officials to identify willing landowners, and then finally some of that ground truthing of potential sites via both soil sampling and some minimal tributary water quality sampling work. And then about 3 years ago, after settling on this Defiance site, we entered the engineering and design phase and awarded the construction contract to begin in fall of 2020. And that work continued into 2021 and also included a period to allow the vegetation to establish and site stabilization before the site became fully operational in March of last year. So I'll use this aerial image of the site to walk through how it functions to treat runoff from Colwell Creek, which drains about 900 acres of mostly farmland in Defiance County, before emptying into the Auglaize River, which is a tributary to the Maumee River, and that joins shortly downstream of this site. So the wetland treatment system is about 9 acres in size, and it begins with a settling pond that diverts a portion of the creek water during elevated flow events. And then a pumping system lifts the water to the first of 4 wetland cells. And that component was necessary because of the elevation differences between the creek and the field were such that it was impractical and cost prohibitive to have excavation for a gravity flow system. And as shown in these dark blue arrows, water then flows through 4 wetland cells, and these are separated by berms that have an earthen weir and an agri-drain that convey the flow between the cells. So flow follows a meandering, slightly deeper channel and then spreads over onto the bench or floodplain areas as more of the water volume fills the wetland. And then finally, at the end of cell 4, water exits the wetland through both an overflow weir and again an agri-drain pipe, discharging into the drainage ditch before that empties back into the creek, really just a few hundred feet downstream of where the water was initially diverted. And so with the next animation, we'll show some of the photos with various features of this wetland system in action during the 2022 season, starting with that photo of some turbid water being diverted into the settling pond in the top left to look at the floats as part of the pumping system. It is a float controlled pumping system based on the water elevations in that settling pond. A nice action photo of water being blasted into the inlet flume there in the middle, and then some other components within the wetland and agri-drain, and then the outlet there on the bottom left. So in the next slide here, we'll use that same aerial image, but this schematic shows the monitoring features, so the various structures and devices that have been deployed to accomplish the monitoring and research objectives of this project. And just after I finish, Chad will be describing the equipment that was installed by USGS. So LimnoTech has installed water level sensors, water quality sondes, online nutrient analyzers, automated ISCO samplers, and a communication tower that gives us both remote access to the pumping system as well as helps communicate much of the data we collect in real time. And there'll be some photos of these various devices as you see here. So in addition to demonstrating some of these technologies and how they might be used in other sites, the primary purpose of these deployments is to help us achieve our research objectives, which those are listed here to determine the water balance for the site and overall phosphorus removal or retention, investigate internal functioning of the wetland, to identify the primary characteristics and operational strategies that promote phosphorus retention, as well as investigate the impact of various management actions on phosphorus retention. And with that, I will hand it off to Chad to describe the USGS monitoring.
Hi, yeah. So I'm Chad Toussaint with the Physical Scientist U.S. Geological Survey. I was the last invitee to this ball of 4 presenters today, but very glad to be a part of it. USGS was approached to look at the mass balance, the totality of what's coming into the wetland and what's exiting the wetland. So some of those early slides that Jacob showed and some of what Derek talked about were kind of like the tie-ins, and then they're more of the functionality within the wetland itself. So today I'm going to highlight some contributions USGS made to the project, including the flow, the monitoring, some information that's publicly available to you guys, so you guys can monitor at least visually what's going on in the wetland, and then some of the workflow that we do to arrive at some of the cold hard numbers that we have accumulated in the last year. So the next slide, which we're at now, I see. Okay, our monitoring process starts before the wetland. We start the monitoring process in Colwell Creek, which Derek kind of alluded to. So this whole graphic here will look very similar to what Derek just described, but I'm going to take it through the approach that USGS is analyzing it. So we use Colwell Creek to get a baseline data for discharge from the drainage area and to assess the nutrient capacity. By collecting this data, we can assess not just what the wetland component is, but the holding pond, which is part of the study design because of the challenges of the lack of elevation. I want to draw your attention though to the hydrologic imagery visualization and information systems, or HIVIS. This is a publicly available system that allows you to view real-time data and photographs. So in this, you can see that we've got pictures, we've got stage. I think there's a discharge component, and as we go through, I'll show you other features that are a part of it. So after water passes through the culvert in Colwell Creek, it goes back into an open channel, but then is diverted into the holding pond. Little graphic here should travel down, and so it gets dumped in the holding pond. and then it's pumped to the start of the wetland, which Derek described a little bit. This is our second sample collection spot. At this central hub, we also collected precipitation data for this site and other met data. So wind speed, wind direction, relative humidity, soil moisture, soil temperature. On the high vis page here, you can see all these little orange dots along here. These are all individual photos that we take that you can view through tracing the hydrograph, or you can view them by a step-by-step process, which on the larger page is pretty evident, where you can click through and then do a step-by-step. Each of these dots, like I said, is a photograph, and then after the water has meandered back through the stream, or meandered through the system, it reaches the outlet, which is comprised of two components: the agri-drain, which Derek alluded to, and the overflow control structure. On that high-vis page, you'll also view the imagery of the video flip by choosing your own date range. So I think we're a couple clicks behind, Tim. There we go. So it meanders through, we get to the outlet, which is on this far side. And then when we get to the high-vis page, so this is the step-by-step process. So you can change your date range, you can do a playback speed so it loops the videos together. And then all wetland sites on this page, if you go to the high-vis, if you type in like Ohio high-vis, it'll take you to a larger page which has multiple sites on it across the state and throughout the country. You can designate by state. And these pictures are available only since the site's been updated. So this new central location's come on in the last several months, but for the wetland specifically, it's been here since roughly mid-November. Next slide. Oh, there's our automatic playback. Yeah, so I'd like to highlight some of the work I've done there. So over the last year, I've made 30 visits to the wetland for sample collection. During this time, we made measurements to verify discharge and equipment to check the stability of each gauge. Sample collection at each gauge is controlled through a processor that can be accessed through a cellular modem. This allows me the ability to adjust frequency or the number of samples collected. USGS analyzed 40 samples at the inlet or pump area. After samples are collected, I use this chart to examine what samples are representative of an event. So up here you can see this blue jagged area, which is our gauge height data, and this is at the central hub, so where it gets blasted out through the pumps. So these little red dots, these vertical red dots, these are all samples taken. So I choose samples that I think are representative of this, what we call an event, a time that the water's flowing and what's not. And then you have these subsequent ones in here, like this very small one, which is second to your left, which is not sampled. And that goes into our, what I call the water accounted for analysis. So at the inflow over the past year, we were able to have samples represent, so these red dots within a event represent 83.4% of flow. So as I alluded to, this section here would be one of the 18.6% or 16.6%, which was not accounted for. At the outflow, we were able to capture 97.8% with 48 samples. My goal for this next year is to try and capture some of these smaller events, because in this time period, it doesn't seem to make a difference, but once in a while you get a quick little event which brings up the retention pond, which then triggers the pumps to go off. And so some of those events are more isolated and may have a larger impact on our final analysis. So my goal is to keep the outflow at a great rate of 97.8 and try to get the other one up to 90. Next, I think Derek is going to talk about the pumping system and what he's discovered internally.
Yep. Yeah. So I'll have a handful of slides here and then hand it back off to Chad once more. So this building on what Chad just shared about the USGS 2020 sampling and showing some snapshots of different events, this slide provides some basic information about the 2022 wetland operations overall, especially as it relates to the pumping system. So the pumping system was activated initially on March 2nd of last year, and that was followed by deployment of the online nutrient analyzers, automated samplers, and water quality sondes a few weeks later. Overall, there were 42 unique pumping events of varying duration. 5 of those events, the largest, were over 40 hours, with the longest lasting around 3 days. And shown in this table, most of the pumping took place in the month of March, followed by May and June, with less in April as it had relatively low precipitation and runoff. And there were a few significant thunderstorms that resulted in events in July and August. But otherwise, the weather and dry watershed conditions did not produce enough runoff to activate the pumping system for the remainder of the year. Next slide. So to help put the 2022 operations into perspective, although we successfully intercepted and treated runoff with this wetland for a number of events, we actually expect more events to happen in average or even wetter years. So 2022 was relatively dry with lower phosphorus loading from the Western Lake Erie watersheds, and because of that, it resulted in a smaller than average harmful algal bloom forecasted for the lake. And as you see in this plot in the bottom left, the annual precipitation at Defiance, shown in the red line, for 2022 was the second lowest in the last 10 years. And really notably, through the end of June, kind of that critical spring period, it was the lowest in the last decade and the lowest precipitation, or second lowest, excuse me, in the last 30 years for that airport. So, despite some meaningful rain events in July and August, you see kind of an uptick in that red line in those months that really led to little or no runoff for those summer months. And as shown in the plot in the bottom right, which is from the U.S. Drought Monitor aggregated for the Auglaize River watershed where the wetland resides, this low precipitation resulted in temporary drought conditions for most of the month of July, which was relieved by those summer storms, but things dried up again in September and October, leading to drought conditions for the remainder of the fall. Okay, yeah, so I'll use these next slides to show some of the preliminary results from those various monitoring equipments that LimnoTech deployed that I described earlier. And what I want to do is focus on smaller windows of time, focusing on 2 periods of back-to-back rain and pumping events. So 4 rain events in total, 2 in early June and 2 in early May, which are shown in the top plot. And during these events, LimnoTech activated those ISCO automated samplers for internal sampling at the ends of wetland cells 2, 3, and 4. And then meanwhile, like Chad described, the USGS was sampling the creek, the water entering cell 1, and then the water leaving the wetland at the end of the 4th cell. And I'll take some time to describe these plots because there's a lot of information and data shown there. So first, on the primary y-axis, we have the continuous time series of inflow. That's the gray color, light gray color. And outflow is the orange. So focusing on the hydrographs, what you can see is kind of the duration of the pumping. That's with the inflow. You have a spike to around 2 CFS, then it ends when the pumps are turned off, and then maybe there's a subsequent spike if some new flow entered the settling pond. Followed by the back-to-back events. And we do see some dampening of that hydrograph. The outflow hydrograph doesn't quite have the same peak flow. And we see a significant lag time of around 12 hours or so between the inflow and outflow peaks, and then some continuing outflow as the wetland slowly drains. And then on the secondary y-axis, focusing on the phosphorus, we have total phosphorus concentrations at 6 different locations throughout the system, starting from the creek and then going through the wetland system and finishing at cell 4, which is the orange square there. So if we click the next animation, I know there's a lot of data to show there that the point of this analysis, or what I want to show here, is to look at how phosphorus concentrations change throughout the entire system. So looking at average concentrations for each event and then these 4 events overall, we have this bar chart that shows that overall there were incremental reductions throughout the entire systems, with relatively higher reductions suggested between the untreated water in the creek, some reduction in the settling pond, and then what happens between the settling pond and the end of the first wetland cell, followed by some, but not as much of a decrease in phosphorus concentrations from the end of cell 1 to the wetland outlet. Next slide. So next we'll take a look at results from those turbidity sensors, which give us continuous measurements of turbidity at different points in the wetland system. And we anticipated this treatment system would be effective at reducing particulates. So looking at these continuous turbidity measurements at the ends of cells 1, which is shown in the green dots or time series, and then cell 3, which is shown in blue. Cell 2 instrument happened to be offline at this period due to an instrumentation issue. So, focusing on these two locations over the course of the event, if we look at cell 1, turbidity really spikes with that first flush of water entering the wetland cell. Shortly after the pumps are activated, that turbid water is making its way to the end of cell 1, which it coincides with the first flush of sediments corresponding to the high flows and increasing flows in the creek and then the settling pond. And so we see a good reduction in those peak or high turbidity levels, followed by some merging of the lines between cells 1 and 3, and that both corresponds to lower turbidity coming into the system, but then also with the inflow or the pumping stopping and water is settling more and more throughout the system, as well as exiting the system without that new inflow. And we have a few photos from these events to the right depicting the relatively higher turbidity in the untreated field runoff in that photo to the far right at the top, as well as early parts of the wetland system, the inlet flume in the top photo and the settling pond in the bottom left aerial imagery, versus relatively lower turbidity leaving the wetland outlet, and that's shown in a few of the different images, both aerial images and on the ground photos. And this demonstrates the effectiveness of this system at reducing particulates. Again, it's something we anticipated, as well as the sediment-bound phosphorus. But its ability to remove the dissolved phosphorus was a remaining question, and really key to what Jacob had described earlier, whether integration of that soil phosphorus sorption capacity analyses as part of the site selection process had any merit. Next slide. So the last results I will show before handing it back over to Chad are from those sensors that were deployed to collect dissolved phosphorus concentrations by the online nutrient analyzers or new labs. And these two devices were located at the inlet to the wetland after the settling pond, as well as the wetland outlet, so slightly different locations in this plot. And the sampling interval was typically 2 hours that were taking dissolved phosphorus measurements at these locations. The inlet concentrations are shown in green and the outlet in blue. And overall, the data suggests that for these 4 spring events over the course of the 4 wetland cells, it is also effective at reducing the dissolved phosphorus. And then we have one more plot here that Tim will bring up. So as this cumulative frequency distribution plot shows, now looking over the course of the entire spring season, you can see the overall difference in dissolved phosphorus concentrations between the inlet, again shown in green, and the outlet shown in blue. So what we were seeing was over a 50% reduction in the median concentration and throughout most of this distribution curve, and really closer to 60% more of reduction in dissolved phosphorus concentrations between the wetland, inlet, and outlet. But everything I presented so far is just concentration. So at this point, I'll hand it back over to Chad to give a full picture from the mass balance perspective work that he's compiled.
Thanks, Derek. Yeah, so we're going to hear it again, but the USGS role in this project was from the beginning to get that mass balance equation. What's entering the system, how much is entering the system, and what and how much leaves the system. USGS can provide the big numbers, but internally, we've relied on our partners in this project, LimnoTech and ERDIC, and those internal mechanisms, which I think Derek covered really well, and Jacob will cover his part later on. Over the next couple of slides, though, I'll present the ins and outs of the wetland. Unfortunately, the data I'm going to present today is only for the for cells 1, 2, and 3. I don't have the data ready to be presented for the effects of the holding pond on phosphorus reduction, but that soon should be incorporated into the overall analysis. It's pretty standard practice for the US or for a GLRI slate of constituents to calculate these 9 in the table shown here. But this is the optimum P wetland. So we're going to focus on the phosphorus and other indicators. The first thing to note is we calculated reductions across the board. At 49% reduction in total P, 24% and suspended sediment reduction, which is usually a substantial indicator of particulate P phosphorus. And then we also witnessed a 69% reduction in DRP. It is well documented that seasonality can have great implications on nutrient reduction expectations. I put together some graphs here to peek at some of the effects of the wetland. One thing that I don't know has been mentioned, but needs to be mentioned, we shut off the pumps from November till the 1st of March. So that's why some data you see here in the November, January area, that's only data we get from the outlet because we still have some precipitation. It can fill up enough to where we get a little bit of outlet data, but I've boxed in the months that we are running the sampler. So keep in mind that March runoff period is heavily based on 2 things. One, the pumps are off from November to March, and there is very, very little to even no vegetation in the wetland by March 1st when the pumps get turned on. So sample total P indicated a reduction every month. With the holding of water and initial flush, the March runoff accounted for 42% of total phosphorus last year. Please note the monthly precipitation trends too, which Derek kind of talked to when he was talking about the precipitation, the drought effects that we saw. Through July and August, though in July and August indicated large rain totals, the events were solitary. So the antecedent conditions were dry and crops were in full evapotranspiration mode, soaking up most of the rainfall. Suspended sediment in the March and April months indicated an increase as water traveled through the wetland, which I think can be probably attributed to bare soil in the wetland. Especially at the outlet, we made some adjustments with the flow control structure at the outlet late last November. So that ground hadn't really received any vegetative growth on it. So it's barren, it's a little disturbed. I think we can contribute the higher suspended sediments to that because in subsequent months it goes down. Water in the pond or water sat in the pond throughout the winter months, gets pumped, and then disturbs that barren soil. Once the vegetation grows, though, we see the water slowed, and we see the reductions in suspended sediment. Particulate P reflects strongly in the trends of total P, where March accounted for 43% of yearly runoff. And finally, dissolved reactive phosphorus showed reductions for every month. But as the inflow of DRP increased in May and June, the reductions became greater. And I think we can attribute that to the wetland vegetation taking a lot of that up. Overall, I think the first year results are extremely positive. The percent reductions, which Jacob alluded to, were pretty much met across the board at that 60-80% range. The last thing I'd like to show you, and we've got a lot of cameras at the wetland, and if you get on that high-vis page, you'll be able to see them, but I think everyone likes to see the wildlife and what kind of critters are being attracted here. So I just put this little slide up. In the upper left here, we got a little groundhog, kind of between the agri-drain and that roped off area. We got a great blue heron, which she or he are there a lot. I was out there last week and they were there too. A little trash panda, or otherwise known as a raccoon, in the bottom left, and then some wild turkeys in the bottom right. The central picture is this egg-laying snapping turtle that I was lucky enough to stumble upon when I was visiting the wetland to collect some samples in June last year, and I got to see her lay her clutch, and pretty neat little event, and that's why you've seen some of these pictures, this squared rope off area, to keep our visitors, people visiting wetland and collecting out of her nest area. I just kind of roped that off, but unfortunately, this past I think it was October, something got in the hole and dug up what looked like remnants of shell. So little guys didn't make it through the summer, but still really neat experience. And I mean, this is one little part of the wetland, so I have a feeling like there's probably some other clutches that got laid out there too. But next we'll turn it back over to, I think, Jacob.
Yeah, thanks, Chad and Derek. Great job to the both of you describing some of the preliminary results. And I think Chad kind of capped it off well there, talking about some of the co-benefits to wildlife. And we do see quite a number of species out there, both fish that get into the settling pond and occupy the wetland, and deer and other terrestrial wetland species using it. To kind of wrap up the preliminary results, I do want to touch on some of the soils work that's going on. We go out in the springtime and then again kind of at the end of the season, and we collect about 120 soil samples across the site on a grid. This allows us to look at kind of the long-term trajectory of the site in terms of where and how phosphorus is being stored within those long-term soil pools. And you can see that in the heat map that's presented in the middle. You can see one of our excellent collaborators, Shailene, collecting soils there in the top right, and then some of the field conditions in the other photos. But we do have the samples stratified across the wetland, both within what we call the channel and the adjacent floodplain. And, you know, the red areas are where we're seeing quite a bit of phosphorus accumulation. We are seeing some areas in this initial phase where some phosphorus is coming out of the soil. And that's not expected. That's not unexpected, given the fact that this was in row crop agriculture for a long time, and there was quite a bit of fertilization that happened at the site during that period. And we do anticipate, getting to one of the comments of the chat, that there will be some flux of phosphorus out of the site following periods where the site is dry, as we get shifts in the redox status and we get some of potential release of some iron-occluded phosphorus with the switching between aerobic and anaerobic conditions. But overall, I think the results are clear based on both the water quality and the initial soils work, that the site has having a very strong net positive in terms of phosphorus reduction. And again, you know, just to emphasize, this is an R&D wetland. So this is built for the purpose of constructing and informing future operations. So how do we maximize phosphorus retention opportunities while minimizing potential release of phosphorus? So we'll be continuing the soils work, looking both at phosphorus retention hotspots, how that relates to hydro period, and then we'll also be in the future years looking at deploying soil amendments to try and recharge some of these phosphorus retention hotspots, to get at those longer-term questions of how do we sustain the use of these systems over periods of 5 to 20 or more years. Getting at one of the comments from, I think, from Andy about life cycle analysis and how do we integrate these systems into the agricultural and urban landscape, and what opportunities are there to kind of build these sites into our long-term best management practices. There's been some papers, including published by Bill Mitch, who worked for a number of years at Ohio State and throughout the region, that these wetland systems provide opportunities to periodically remove small portions in strategic locations out of agricultural production, and then roll those areas back into agricultural production after they've played a role in reducing nutrients and capturing nutrients that have been placed onto the landscape. So quite a bit of work going on during the last year across kind of the mass balance that Chad talked about, the internal phosphorus retention that Derek touched on, and then a longer time scale applications in terms of the soil retention of what's going on with phosphorus throughout the site. With that, I will ask Tim to go on to the next slide, and I want to touch a little bit on tech transfer activities because all the research that's gone on in the journal papers that have been published, et cetera, they all have value, but a big emphasis within the team and within our funding partners at the EPA and GLRI is outreach and tech transfer. And so that has been a major emphasis for this group, is trying to get information out to a variety of audiences And that includes the kind of academic, scientific community, but also really we're targeting the practitioners and the landowners in the region. And so that's being done through both journal publications, but also a number of conference presentations, importantly, events like this one today, and outreach events, working with regional partners, with groups in the Western Lake Erie Basin, the LEARN Network, which is associated with the H2 Ohio program, and also doing things like publishing or putting out YouTube videos and social media posts to try and target a diverse group of folks. And then we're really moving into the phase now that we have some preliminary data of really trying to highlight operational guidelines and technical guidance for the practitioners in the region. And then, that all, we really work hard to push that out through local news outlets to really maximize our impact. And of course, none of this would be possible without partnership with the City of Defiance, our funding sources at GLRI, and many others that you see on the screen here that have helped us over the years get where we are. With that, I will turn it back over to you, Tim, to lead the Q&A for the remaining section, or period. Thank you all for joining today.
Yeah, thanks, Jacob. And I'll just jump off your outreach piece here a little bit as well. As we mentioned, we did invite some folks out to the wetland this past April. Had a really in-depth, kind of exciting, hot day out in the field, kind of looking at how the wetland operates. Those opportunities will come up, but really, we are looking for opportunities to, share this research and integrate it into other activities that you all on the line might have going on at the state and local level. So we really kind of, we do want to emphasize this outreach piece because it's really important to us and it's really part of our goal. I did mention that this webinar is recorded. We are building a project website that we intend to place this webinar and a lot of this information you see linked on here on that website. So that's something you can stay tuned with. We'll go to questions, and I did put my email in the chat for anybody that has questions, interest in the project after today. Please look in the chat and grab my email out of there. But with that, I think, I'm going to go to the next slide here. We do have these basic sort of charge questions, which are, kind of intended to, introduce some thought and some perspectives from outside of our team. So feel free to respond to these if you'd like. But with that, I know we did have some questions back early on. I think the first ones, I don't know if Derek or others were able to answer it. From Larry Antosh in regards to retention times at the cell, and are they being managed or free flowing? That might be a question for Derek.
Yep, sure. I think I put a response in the chat there later. So really, water moves pretty quickly through the wetland system overall, but it's on the order of 3 to 4 hours of retention for an individual cell. Like I put in the chat, it's not actively managed. We do have the capability to raise or lower boards within the agri-drain to hold back more water or let it go. But again, that's not an automated system, so those would be manually changed.
Yeah, thanks, Derek. And I see some questions that I think you've answered in regards to cell profile, also in regards to permitting. So those answers are in the chat. We'll leave a quick space if there's anything you want to add to those here.
No, I think between, Jacob was answering some of them on the fly too, I believe. So between that and the chat should be good there. This last one I'm seeing on what was considered in determining the size of the feature and number of cells. Later cells seem to have diminishing returns. So great question there. Really the size of this overall wetland.
May have lost you there for a second, Derek. Jacob or Chad, are you guys still with us?
Yeah, I'm here.
I am.
Tim, I'll try. I'll try and jump in.
Back.
Yeah, are you back, Derek?
Yeah, let me stay on video off. Can you hear me?
Gotcha now.
Okay. Sorry about that. Yeah. So I forget where I left off, but I was talking about the size of the wetland, and basically it was trying to work with, the available land that we had to have as large of a wetland within the resources available, and the just the elevations of the field. So, the comment about later cells having diminishing returns. We'll keep, again, these were preliminary results. We'll keep evaluating if that changes over time. One of the things from the TNC wetland work that Jacob was looking at, and he could comment more on, is what we're hoping or might see is that actually because most of the removal may be happening in the first part of the system, that might reach a capacity over time. And then over time, if there's less removed in the first wetland cell, that means there's higher phosphorus entering cells 2 and 3 and 4. And if there's higher entering, that potentially means more of it could be reduced into subsequent cells via either absorption or settling of the solid. So a great question. It's pretty early, I think, to make conclusions one way or the other on how it's functioning, but yeah, hopefully that can provide some insights.
Yeah, thanks, Derek. And a good one in here from Sandra. This might be a question for Chad. Are you measuring the loads and concentrations in the stream? How much of the stream flow is getting captured and sent through the wetland? What percentage of it are you trying to capture? I'm not sure, Chad, if that might be more up your alley.
Yeah, I was actually just messaging Sandra, but I can speak on it now. We are monitoring the stream. I mentioned in the presentation earlier that I don't have that data ready. The stream's pretty tricky to get some of the discharge finalized because it is almost constantly in a backwater condition. So it takes special equipment to do that. And we've had that installed the whole time, but getting that data hashed out and verified for accuracy is taking a little longer than I want to. But we are taking concentrations. It receives the same amount of scrutiny and collection as the internal sites that we have, or the sites at the inlet and the outflow. As far as percent captured, it's going to be very high because there's a slight, so when the water gets diverted into the settling pond, there is the ability for, in really large events, for it to go over top of a embankment that we created that does have a pipe underneath it that could allow really low flows to go through. I haven't witnessed that, so really the only water we're missing is in flood conditions. And since we started monitoring last year, I think we had one event that could have happened. But again, the entire system goes into backwater at that time, so there isn't a lot of discharge or flow moving around the wetland at that time or evading the wetland. So with the next couple months, I will definitely have that data and I can update the group, or you can reach out to me if you're still interested at that time, and I will try to get that to you then.
Yeah, thanks, Chad. And maybe one more question here from Michael. Similar question. I'm not sure if we have the answer to the second part. What can you extrapolate on percentage of wetlands in the landscape required to achieve nutrient removal goals? Curious if the team could respond to it, and while they're thinking on it, definitely recognize this is a demonstration wetland. It's a highly sort of built up and research style wetland, not something that would be replicated on a landscape scale. But I think there's opportunities for this type of technology in other wetland restoration work going on across the basin. So I think that's where an opportunity may lie. But I'll hold here and see if the team has any thoughts on the percentage of wetlands at a landscape level.
Yeah, Tim, I'll just make one quick comment, and then the others may have an opportunity. So this also gets at the previous comment and the comment, I believe, from Kendra regarding permits. At no time do we dry out the creek. That was one of the included items in the permit, was that we would not sweep 100% of the water from the creek to provide habitat for biota downstream of the wetland. And in terms of the percentage extrapolation, I don't think that we're there yet with the data analysis. I will say that I referenced earlier some of the work done by Bill Mitch, and he's published papers about this region, suggesting that between 5 to, I believe, somewhere around 10% of the landscape, if that were all converted to wetlands, periodically over time that could address the nutrient reduction goals. Our information is more targeted on how to maximize nutrient retention with systems where we have some operational capacity. But we will, throughout the course of the project over the coming years, be able to speak to removal efficiencies and have some more information about those type of extrapolations. So, Michael, I hope that addressed your question to the extent possible at this time. And I'll turn it back over to you or Tim if others have comments on that.
Yeah, so Derek alluded to a little bit that, we've done 1 year and we had drought conditions, or unusual rainfall, lower than expected. So to draw those conclusions about extrapolation, it takes years. I mean, that's why this project is planned for 4 to 5 years of research. I don't know if it was mentioned in the project, but this drains a 800-acre basin, and then the active wetland area is 6.5 acres, something similar to that. So it gives you an idea of like what our expectations were, what the capacity of that wetland could hold as far as drainage area. And also to follow up on Jacob's comment about not drying out the stream, the under pipe was put on for that purpose, but that stream it's ephemeral. It does go dry during dry conditions. And this year it was dry for months on end. So that's a natural process that just happens with this particular watershed.
Yeah, thanks, Chad, for adding on that, and Jacob. And with that, I know we're on the time. I'm actually a minute or two over here, so I think we'll kind of hold questions for there. Do look in the chat. You'll see both Jacob's email address and my email address in there if you have any questions or interest to collaborate. Like I said, we're really trying to share this information, work the findings into other opportunities, other wetland restoration work that may be going on in the basin. So please do reach out, or if you have interest in future webinars or getting out and seeing the site for one of our visits. And Chad, yeah, thanks. You got your email in there too. So with that, thanks to everyone for joining us today, and thank you for the team. And I will send out an email link of this recording once we get it on our website, which is also under construction as well. So thanks everybody again, and I hope you all have a good day.